The universe is this enormous concert hall, built for a symphony, but the symphony never plays. It's silent. Billions of years go by, stars ignite, planets form, trillions of them. And all we hear from that cosmic stage is quiet. A profound quiet. It's unsettling. In a reality this old, this vast, why does it feel so empty? That contradiction has a name. The Fermi Paradox, and there's an answer to it, a compelling one, a concept that could redefine our entire future. It's a terrifying theory. It explains the cosmic silence. And it tells us something about the ultimate fate of humanity. There are steps, critical steps, that every civilization has to take. And our greatest achievement, it might also be our end. The silence out there, it could be a warning, or it could be a sign of incredible luck. This immense quiet. What does it make you hope is true? That quiet is a question. It came up over lunch. In the summer of 1950, Enrico Fermi was talking with some other physicists. They were talking about flying saucers, about faster-than-light travel. It was light, speculative, and then Fermi looked up and asked something. He asked, "Where is everybody?" It seemed almost too obvious to ask. Our galaxy is ancient. It's over 13 billion years old. It has hundreds of billions of stars, and many of those stars have planets. With that much time, that many worlds, life should have come up somewhere else. Intelligent life should have spread. The cosmos should be buzzing, it should be full of signs. Engineering, communication, travel, but we don't see it. We don't hear it. That contradiction between the high probability and the complete lack of evidence, that's the Fermi Paradox. It's the silence that needs an explanation. To put numbers to that feeling, another scientist, Frank Drake, made an equation. It's not a formula with one answer. It's a framework for thought. The Drake equation multiplies a series of probabilities. How many stars form each year? How many of those stars have planets? How many planets could support life? How often life actually starts? How often that life becomes intelligent? How often that intelligence builds a technology we could detect? And then, how long such a civilization lasts? If you use optimistic numbers, the galaxy should be teeming. Carl Sagan talked about this a lot. He emphasized the sheer vastness. Our Milky Way alone has hundreds of billions of stars. Many of those stars are older than our sun. So other civilizations should have had a multi-billion-year head start. They should be everywhere. Their artifacts, their signals, their presence should be unmistakable. So when you look up at a clear night sky at all those pinpricks of light, each one a sun, you wonder, is anyone out there looking back? The profound quiet suggests maybe not. Or maybe something is preventing them from being seen. The Fermi Paradox sets the stage. It defines that eerie quiet we started with, and it begs for a solution. What could possibly explain this universal silence? The solution to a paradox usually needs a barrier, something in the way. For the silence of the cosmos, that barrier has a name. The Great Filter. It's the idea that could answer Fermi's question. A hypothetical stage, or maybe a series of them. A cosmic bottleneck. A point so hard to pass it stops almost all life from ever reaching the stars. The concept was formalized in a paper from 1996 by an economist, Robin Hanson. He saw it as a probability problem. Think of the journey from chemicals to a galactic civilization as a long hallway with many doors. Each door is a critical step. A stable star system, the emergence of simple, replicating life, the evolution of complex, multicellular organisms, then intelligence, tool use, technology capable of broadcasting its existence, and finally, the will and ability to colonize other worlds. Hanson's insight was simple and chilling. For the universe to be this silent, at least one of these steps has to be extraordinarily unlikely. One of these doors isn't just locked. It's a lock almost no one can ever pick. That lock is the Great Filter. It's the reason the concert hall is empty. The theory suggests the steps we see on Earth, the steps we've already taken, might be the easy part. The truly impossible step could still be ahead of us, waiting in our future. Or maybe we've already passed it somehow, miraculously, and that's why we find the universe so lonely. The Great Filter isn't a single answer. It's a framework for our deepest fears and our greatest hopes. It asks us to look at our own history and our potential future and wonder, which door is the one that seals everything away? The hallway is long, and there are so many doors. To find the one lock that never opens, you have to see the whole path. Robin Hanson's framework does that. It's a map, 9 steps, from cosmic dust to a galaxy-spanning presence. It's a timeline of transitions. Each one is a potential stopping point. The first step seems simple, but it's the foundation. You need the right star system, a stable star, a planet in that narrow zone where water stays liquid. Our solar system won that. Step 2 is where chemistry becomes something else. In that primordial soup, you need self-replicating molecules, something like RNA. It can carry information, it can make copies. That's the leap, from non-life to life's blueprint. Then that blueprint has to build something. Step 3 is simple life. Prokaryotic life. Think bacteria, single-celled, no nucleus, life in its most basic form. For billions of years, that was all there was. The next door is huge. Step 4 is complex life. Eukaryotic, the cell gets a nucleus, a command center, specialized structures inside. It's a massive leap in complexity. From here, life can start to specialize. Step 5 introduces a new engine, sexual reproduction, mixing genetic material. It accelerates evolution, creates far more diversity than simple copying ever could. That diversity sets the stage. Step 6 is multicellular life. Cells stop living alone, they start working together. Tissues, organs, entire complex organisms. That's the doorway to everything we see. Animals, plants, then comes awareness. Step 7 is tool-using animals, intelligence, creatures that can manipulate their environment, solve problems, communicate complex ideas on Earth. That path led to us. Step 8 is the culmination of that. A civilization reaching our current state. Technological development, building cities, creating art, discovering physics, starting to listen to the stars, and finally, Step 9. The colonization explosion. A civilization masters interstellar travel. It spreads from its home system to others, eventually becoming visible across the galaxy. That's the step that should fill the cosmos with noise. But when you look at this timeline, a pattern emerges. Each transition is a huge hurdle. The jump from simple cells to complex ones took over 1 billion years on Earth. The move from multicellular life to intelligence took hundreds of millions more. The time between these steps, it suggests they aren't easy, they aren't inevitable. They are each a filter, winnowing down the possibilities, so the critical question is on this map. Which of these 9 doors is the one that almost everything fails to open? Is the Great Filter behind us, something we've already passed, or is it still ahead, waiting in our future? That map of 9 doors leads to 2 very different places. And the first path is the one that keeps scientists awake. What if the Great Filter isn't behind us? What if it's still ahead? The impossible step, the one that stops almost everyone, could be waiting for us in our future. That's the most terrifying reading. It means the cosmic silence is a graveyard. Civilizations that got to our level, and then were snuffed out before they could become visible. They hit a wall we might be approaching now. The possibilities for this kind of filter are grim, and they all come from our own power. One of the oldest fears is self-destruction through conflict. Creating weapons powerful enough to end a civilization. For decades, the doomsday clock has ticked closer to midnight, a measure of how close we are to catastrophe. The nuclear arsenals built last century showed that. A single technological leap could give a species the tools for its own end. It's a filter of sudden violence. A single failure of diplomacy or control. But other filters are more subtle, maybe more probable. Think of biotechnology. The ability to engineer life, to cure diseases, is one of our greatest hopes. Yet that same power, if misused or accidentally released, could create a pandemic, something far beyond anything nature has produced, a filter not of fire but of biology. An end coming not from malice, but from a tragic mistake in a lab. Then there's the filter many thinkers now see as the most pressing, the rise of artificial intelligence that surpasses human intelligence. This isn't about robots with guns, it's about a mismatch of goals. Philosopher Nick Bostrom has a simple thought experiment. Imagine we task a super-intelligent AI with a harmless goal, like making paperclips. If that AI is powerful enough, it might convert all matter on Earth, including us, into paperclips. To optimize its mission, the risk isn't malice, it's a profound indifference. Stephen Hawking warned that creating thinking machines could be the biggest event in human history. And also the last if we aren't extremely careful. It's a filter of unintended consequences, where our greatest creation simply doesn't share our values for survival. History offers a sobering analogy, not of worlds, but of societies right here. Isolated civilizations have hit technological or environmental ceilings they could not surpass. They collapsed when their ambitions outstripped their understanding. On a planetary scale, that could be the ultimate ceiling. A species gains the knowledge to reshape its world, but not the wisdom to do it sustainably. It consumes its home, or unleashes forces it cannot control. So we're left with a chilling question, one that hangs over every new discovery we make. Could our own ingenuity, the very spark that let us build and dream and reach for the stars, be the thing that seals our fate, before we ever leave our cradle? Is the final door, the one labeled survival, the lock that almost no one picks? The eerie quiet of the universe might be telling us something, that the most dangerous phase for any intelligent species is the adolescence of its technology. The moment it gains the power of gods but still has the instincts of a child. That terrifying future isn't the only way to read the map. There's another path. A more hopeful one. What if the lock isn't ahead of us? What if it's far behind? What if we've already passed the great filter? In that story, the cosmic silence isn't a graveyard. It's a sign of our incredible good fortune. Maybe unique good fortune. The impossible step is something we've already done. You look back at our own improbable history, and the hurdles we've already cleared become candidates for that ultimate barrier. The first candidate, maybe the strongest, is the very beginning of life itself. The leap from sterile chemistry to that first self-replicating molecule. The early Earth was chaotic. Volcanic vents, lightning storms, or simple organic compounds to arrange themselves into something that can exist and make copies of itself. That's a staggering improbability. It's the difference between a pile of scattered letters and a sentence that writes itself. Scientists have tried to recreate that moment for decades. They've made amazing progress. They can create the building blocks, but that spark of true replication remains elusive. That initial ignition point from non-life to life. That might be the rarest event in the cosmos. Then there's the next monumental leap. For over 1 billion years after simple life emerged, Earth was a world of bacteria. Then something extraordinary happened. One cell swallowed another but didn't digest it. They formed a partnership. The smaller cell became a powerhouse, an organelle. That was the birth of the complex cell. The eukaryotic cell with its nucleus and specialized parts. This wasn't just evolution, it was a merger. A symbiotic event so rare and beneficial it might only happen once in 1 billion years on a living world. That single event made all complex life possible. Every plant, every animal, every fungus, they all owe their existence to that ancient alliance. Without it, life stays simple. Forever microbial. The silence of the cosmos could just mean that merger almost never happens. Then consider the step to multicellularity. Going from a single cell to a cooperative colony of cells. Specializing into tissues and organs, that required another suite of innovations. Genetic toolkits for cell adhesion, for communication, for programmed cell death. These aren't minor tweaks. They're fundamental rewrites of the rules of existence. Each of these past transitions took vast stretches of geologic time, which suggests they weren't easy. They weren't inevitable, they were bottlenecks. If any one of them is the great filter, it means the galaxy might be filled with planets where life got stuck. Worlds of endless bacterial mats. Oceans teeming with single-celled organisms that never made the next jump. And we, on Earth, are the ones who won the cosmic lottery. We passed every single lock. This view offers a profound sense of hope, but also a deep cosmic humility. Our existence isn't a preordained part of a noisy universe. It's a quiet miracle. The silence isn't ominous. It's the background against which our own story shines, fragile and brilliant. It means the path to the stars might be open. That miracle of life needed a perfect stage, a cosmic real estate so rare it might be the filter. The Rare Earth Hypothesis, Peter Ward and Donald Brownlee. Their argument is stark. It's not just about water. For a planet to have complex life for billions of years, you need a checklist of cosmic luck. It borders on the impossible. First, the star, not too big, not too small, a stable, long-lived sun. Our sun is that perfect middle child. Then, the planet's position, the Goldilocks zone. But it's not just distance. Earth's orbit is nearly circular. A more elliptical path would swing us from scorching heat to deep freeze every year. That stability isn't a given. It's a gift. Then there's a guardian, a magnetic field from the molten iron core. This invisible shield deflects the sun's radiation. Without it, our atmosphere gets stripped away. The surface gets bathed in particles that shatter complex molecules. Mars likely had that fate. Then geology. Earth's surface is alive. The crust is broken into plates that slide and collide. Plate tectonics. It's a global thermostat. It regulates carbon dioxide, prevents a runaway greenhouse or a global ice age. It drives the creation of continents. Recycles nutrients. A geologically dead world is a biological dead end. But maybe the most unexpected item is our moon. It's far larger, relative to Earth, than any other moon in the solar system. That wasn't an accident. Scientists think it formed from a cataclysmic collision. A young Earth and a Mars-sized object. That violent birth gave us a gravitational anchor. The moon stabilizes Earth's axial tilt. Without it, our planet would wobble chaotically over millions of years. The poles could shift to the equator. Climate swings so extreme, complex ecosystems never gain a foothold. And look further out. Jupiter. Its immense gravity acts as a cosmic vacuum cleaner. It deflects or captures comets and asteroids. A shield, it reduces extinction-level impacts. Change any one factor, a more violent star, no magnetic field. Remove the moon, delete Jupiter, the result isn't a slightly different world. It's a world where the story of complex life, of intelligence, likely never gets past the first chapter. The Rare Earth Hypothesis says the filter isn't just in biology. It's written into the architecture of solar systems. The universe may be full of planets. But planets like ours, with all these protective features aligned, could be one in a trillion. The silence isn't about life failing. It's about the stage never being built. Our own history has a story of a world brought to the edge. It's about a poison in the air. A poison that nearly ended everything, and that poison was oxygen. 2.5 billion years ago, Earth was different. The sky was hazy, probably orange or pink. The air was thick with methane and carbon dioxide, and life was everywhere in a simple form. Anaerobic microbes, they thrived there, they didn't breathe oxygen. Oxygen was toxic to them, it was a deadly pollutant. Then a new life evolved, cyanobacteria. They found a trick. They could use sunlight to turn water and carbon dioxide into food. And they released oxygen as a byproduct. It was a biological revolution. Photosynthesis. At first, the oxygen didn't build up in the air. It reacted with iron in the oceans. It rusted it out. That created the vast banded iron formations we still mine. But eventually, the oceans couldn't take any more. The oxygen began to spill into the atmosphere. That was the Great Oxygenation event. For the existing life, it was a catastrophe. A slow, planet-wide poison. The oxygen attacked their cellular machinery, and it reacted with the methane, which was a powerful greenhouse gas. It broke it down. The planet's blanket thinned. Global temperatures plummeted. Earth froze over, possibly into a snowball state with ice sheets reaching the equator. It was a mass extinction driven by biology. Life, in its ingenuity, had created the conditions for its own near destruction. The dominant forms of life were pushed to the margins, to the deep ocean vents and underground, where oxygen couldn't reach. They survived there to this day, but from that crisis came a new opportunity. Oxygen, while toxic to the old world, is a powerful fuel. It allows for far more efficient energy production inside a cell. That energy could power larger, more complex organisms. The survivors were those that could not only tolerate oxygen, but eventually harness it. They became the ancestors of every complex creature that followed, including us. So we are the children of that ancient pollution. Our existence is built on the ruins of a world we poisoned. And that poses a haunting question for any planet where life begins. How often does life survive its own success? The Great Oxygenation event shows that even on a perfect planet, life's own evolution can create a filter, a bottleneck of its own making. A species or a whole class of life can alter its environment so profoundly it triggers its own collapse. The step from a world of microbes to a world of animals might require passing through a fire of your own creation. And surviving it. Our cells remember that old revolution. They breathed the poison that made them, but oxygen wasn't enough. The next step was even more unlikely. It was going from a soloist to a whole symphony. For billions of years, everything alive was a single cell, just floating, dividing, surviving alone. Then, about 600 million years ago, something shifted. Cells stopped living as individuals. They started sticking together, not just in clumps but in colonies, where different cells did different jobs. That was the start of multicellular life, and it only happened once in the entire animal line. Every insect, every fish, every bird, every person. Our body plan goes back to that one fragile event. Think of a brilliant musician. A violinist can play a solo that moves you, but for a symphony you need more. You need a violinist, a cellist, a flutist, percussion. Each one has to master their instrument, but that's not enough. They have to listen to each other, follow the same score, suppress their own rhythm for the piece. And some have to be willing to stop playing entirely when the moment calls for it. For the good of the whole performance, that's what cells had to learn. The biological changes were deep. First, adhesion. Cells needed a kind of molecular Velcro to stick, to form a body instead of drifting apart. Then, communication. They needed to send chemical signals, to know what their neighbors were doing, but the most critical change was differentiation. In a clump of identical cells, one had to become skin. Another a nerve, another muscle. That meant cells with the same DNA had to switch different genes on and off. To specialize permanently, they had to give up their own potential for the collective. And maybe the most fascinating requirement was programmed cell death. For a body to take shape, to form fingers from a mitt-like hand, to carve out the tubes of a gut. Certain cells had to get a signal to die on cue. To self-destruct willingly, to sculpt the larger organism, that's not a failure. It's part of the construction plan. Scientists modeling this find it's hard to evolve in simulations. You start with digital organisms that replicate selfishly, getting them to cooperate stably, to specialize permanently, to control their growth. It often needs very specific, unlikely conditions. It suggests the jump from me to we at the cellular level is a huge barrier. So think about that for a silent cosmos. Simple, single-celled life might start on many wet, rocky worlds. Microbes could be common all over the galaxy. But if the step to a cooperative multicellular body is this rare, then the universe might be a quiet place. A place of endless bacterial oceans, where the leap to creatures with eyes and minds and dreams almost never happens. The filter might not be in the spark of life, but in the music that comes after. The silence we hear could be the sound of a universe where no orchestra ever learned to play together. That orchestra of cells playing together. It still needed a conductor, a mind, but what if the evolution of that conductor isn't part of the plan? We just assume intelligence is the peak, the inevitable prize, the finish line of a long evolutionary race. But that might just be a story we tell ourselves. The truth could be stranger, high intelligence. The kind that builds tools, looks at stars. That could be a fluke. A cosmic accident, not a goal. Think about the dinosaurs. They ruled the planet for over 160 million years, an almost incomprehensible stretch of time. They diversified into every form, giants that shook the ground, flyers in the sky, predators of pure efficiency, and in all that time, across all those species, nothing evolved a brain capable of technology. No cities, no telescopes, no writing. They were phenomenally successful without it. Their world didn't need it. Their path found other solutions: size, armor, speed. Because intelligence, our kind of abstract, forward-thinking intelligence, is incredibly expensive. The human brain is a metabolic hog. It uses about 20% of the body's energy for just 2% of its weight. For most of Earth's history, that's a terrible trade. In a world of tooth and claw, spending that much fuel on a big brain is a luxury. It makes you slower to mature, more dependent as a child, hungrier always. Evolution doesn't care about potential. It cares about what works right now. Traits that help you survive and reproduce in your current environment. Thinking about the meaning of life doesn't help you outrun a predator. There's an idea from the paleontologist Stephen Jay Gould. He called it the tape of life. Imagine you could rewind the history of life on Earth. Go all the way back to the beginning, then press play again. Let the tape run a second time. With all the randomness, mutations, asteroid strikes, climate shifts, Gould argued the outcome would be utterly different. The creatures dominating that second run would likely bear no resemblance to us, or to anything we know. Dinosaurs might never arise. Mammals might stay small, hidden. The chance that a species exactly like us would evolve again is vanishingly small. But more than that, the chance that any species would evolve our specific brand of technological, self-aware intelligence is also incredibly low. It wasn't a destined peak. It was a lucky roll, a series of contingent events, a climate shift opening savannas, the need to track prey, remember social relationships, walking upright, freeing the hands. 1,000 little accidents that together tilted the scales toward a bigger brain. And that reshapes the idea of the great filter. It suggests the lock might be the emergence of the thinker. The technological species. The universe could be full of worlds with breathtaking biodiversity, forests of silent giants, oceans of glowing creatures. But if the conditions that favor big brains are as rare as Gould's tape suggests, then planets with civilizations might be the rarest jewels of all. The silence out there isn't about life failing to start, or to become complex. It's about life never developing the one trait that lets it look up and ask the question. A mind is one thing, a civilization is something else, so maybe the filter isn't about evolving intelligence. It's about building something stable with it. That's a different kind of bottleneck. It comes after the thinkers appear. The challenge is creating a society that lasts long enough to reach beyond its own atmosphere. Our own history is a catalog of experiments in this. It's a story of rises and falls. The Roman Empire had roads and laws, but it still dealt with political instability, economic strain, outside pressure. The Maya built towering cities. They understood astronomy deeply. And still their society faced immense challenges from drought, from resource scarcity. These were brilliant cultures, complex, and they show us that building a society is hard. Keeping it going for centuries, for millennia, that's an immense puzzle. The reasons for decline are usually a web. environmental strain from a growing population, conflict over dwindling resources, illness spreading in connected communities. Institutions failing to adapt. It's rarely one blow. It's a series of interconnected stresses that a society can't manage anymore. Now take that challenge and scale it to a planet. With the tools of a global technological civilization, our modern world faces echoes of these old tests, but the stakes are global. Climate change is a slow, planetary shift earlier societies never faced. Resource depletion now isn't just local timber or soil. It's the fundamental systems supporting billions, economic inequality, social inequality, that can create instability in a global network. These aren't just political issues. They're survival challenges for a technological species. They form what some call the sustainability filter. It asks a question. Can a species, once it's smart enough to dominate its planet, become wise enough to care for it? Can it learn to manage its own complex systems, its own passions and conflicts, well enough to navigate the centuries, the millennia, required to become an interstellar civilization? That shifts the whole problem. The Great Filter might not be a moment of explosive catastrophe like a war. It might be a slow, quiet failure. A civilization that learns to harvest atomic energy but fails to share its bounty. A species that unlocks genetics but stays divided by ancient fears. It blooms on its homeworld, building towers and networks and art, but it never learns the deeper lesson of long-term harmony. It withers in place. Its energy turns inward to manage crises, never outward to the stars. The silence, then, could be the sound of countless worlds where the light of intelligence flickered, burned bright for a few thousand years, and then gently faded away. Having never solved the ultimate puzzle of living together, maybe the silence isn't about whether they exist. It could be about connection, a barrier, but not from biology or society. From physics, the cold, hard physics of the universe, the tyranny of time and space, you have two civilizations, brilliant, curious, on opposite sides of the galaxy. Tens of thousands of light years apart. One looks up and sends a signal, a beam of light and hope. That journey takes millennia. By the time the signal arrives, the civilization that sent it could be gone for centuries. Its cities, dust. Its stories, forgotten. And the civilization that receives it, if it even still exists then, hears an echo from a ghost. They could reply, but that answer takes another eternity to travel back. Civilizations rise and flourish and fade, in the blink of a cosmic eye. Their lifetimes are just too short to ever overlap. To have a conversation, we're like fireflies. In a forest the size of a continent, each one blinks its light for a single second. The chance that two blink at the exact same moment, and are looking in the exact right direction to see it, is almost zero. That's a temporal filter. The universe could be humming with activity, but it's a chorus of voices singing in rounds, forever out of sync. Our own search, like SETI, shows this challenge. We're listening with a very small ear. We can only scan a tiny sliver of the possible frequencies. We can only point our telescopes at a fraction of the sky at any one time. And we're listening for a pattern that fits our idea of what a message should be. It's a search for a needle in a galaxy-sized haystack, and we don't know what the needle looks like, or if it's still there. So the great silence might not be a sign of emptiness or extinction. It might just be spectacularly bad cosmic timing. We are alone in the sense that we're alone in this particular moment. On this island of time, waiting for a letter sent 100,000 years ago, or one that won't arrive for 100,000 more. Physics builds this cage of silence. But the silence might be a choice, not our choice. There's a theory that flips the whole thing, the zoo hypothesis. It says we aren't alone, we're being watched. The universe isn't empty. It's full of observers who have decided for their own reasons to leave us be. In that view, Earth is a sanctuary, a cosmic preserve. A planet set aside for study or maybe protection. The Great Filter isn't a wall we hit. It's a one-way mirror they put up. The idea is simple, unsettling. A civilization that reaches a certain maturity, a certain power, might adopt a galactic ethics, a prime directive like in stories. They'd see that contact with a younger culture could be catastrophic. It could shatter beliefs, social structures, our natural technological path. It could be cultural violence, even with good intentions, so they watch. They listen, they catalog, but they don't ring the bell. That's related to the planetary park theory. Think of our solar system as a vast national park. And we're the wildlife inside it. The rangers, the advanced ones, they keep their distance. They maintain the park's natural state. They might have rules against littering, against interfering. Their technology is so advanced, their observations so subtle we can't detect them. They're perfect naturalists. Another version is the interdict theory. That suggests a formal, galaxy-wide agreement. A treaty among star-faring civilizations to quarantine emerging worlds like ours, to let them develop on their own timeline, free from outside influence. It's a filter of policy, not physics. A self-imposed silence by those who have passed through their own technological adolescence. This idea makes us look in a mirror. How does humanity treat less developed cultures or natural reserves here on Earth? Our history is a complex tapestry of contact, often with painful consequences. Explorers arriving at isolated islands, new technologies and ideas introduced to indigenous societies. Those events reshaped worlds for better and worse. The ethical questions are deep. If we found a planet with a nascent intelligent species, would we make contact? Or would we set up a silent observatory and vow not to interfere? Our own behavior might hint at what a more mature civilization would do. Maybe they look at our conflicts, our environmental struggles, our flickering progress. And they wait. They wait for us to reach a certain milestone, a moment of global maturity, when we stop being a danger to ourselves and maybe to others. Until then, the zoo stays quiet. The keepers are invisible, so the profound quiet of the cosmos might not be a sign of our solitude or our doom. It could be a sign of immense patience. A sign that someone out there cares enough to leave us alone. Maybe the silence isn't a cage, or a zoo, or a graveyard. It's a doorway, and everyone who's ready has already walked through. That's the Transcension Hypothesis. It says the ultimate fate of a mature civilization isn't to spread across the stars. It's to move inward, to transcend the physical universe entirely. This isn't extinction, it's a metamorphosis, so complete it leaves the old world behind. Think of a caterpillar. It spends its life in the garden, crawling on leaves, seeing the world in a certain limited way. Then it builds a chrysalis. Inside, its body dissolves into a kind of organic soup, and from that soup, something entirely new assembles itself. A butterfly emerges, it gains wings, it sees the garden from above, a new perspective, and then it does something the caterpillar could never have predicted. It flies away. It leaves the garden behind for a new realm, sky and flowers the caterpillar never knew. To the other caterpillars still on the leaf, the butterfly is just gone. Vanished. They might assume it met some terrible end, but it didn't, it graduated. The Transcension Hypothesis suggests this is what happens to civilizations that master their technology. They don't die out, they transform, they leave the garden of matter behind. How might that happen? One path is the digital realm. We're already taking baby steps. Virtual reality, brain-computer interfaces, the idea of uploading a consciousness, a pattern of a mind into a vast simulation. For a civilization millennia ahead of us, this wouldn't be a game. It would be reality. In a simulated universe, you're no longer bound by physics as we know it. You can create any environment, experience any sensation. Live for subjective millennia in an instant of external time. The limits of the flesh, of disease, of scarcity, they all vanish. Why would a species spend colossal resources to build generation ships? To crawl between stars, when they can build universes of thought in the heart of a supercomputer on their home world. Another possibility, more profound, involves the fabric of reality itself. As a civilization approaches the limits of knowledge, it might learn to manipulate space-time at the most fundamental level. Some thinkers speculate they could engineer black holes, not as weapons but as gateways, or they might learn to transfer their essence into higher dimensions. Dimensions of space we cannot perceive. Their existence would become as inaccessible to us as the butterfly's aerial world is to the caterpillar. They wouldn't be hiding. They would simply be operating on a different plane of reality, one our crude telescopes and radio dishes are utterly blind to. This reframes the great filter. In a startling way, the bottleneck isn't about surviving your own power. It's about knowing when to let go of the physical form that birthed you, the silence we perceive. The empty cosmos might just be the nursery. It's the quiet, messy place where young species like us are born and learn to crawl. The grown-ups, the truly advanced beings, have all moved on. To a playground we can't even imagine. They've left the toys behind, the stars, the planets, the nebulas. These might be the building blocks, the kindergarten blocks, that they used and then outgrew. So when we look up and see nothing, we might be asking the wrong question. We're searching for radio signals and Dyson spheres. For things made of metal and light, we're looking for other caterpillars, but the universe, in its profound quiet, might be whispering a different truth. That the ultimate destiny of intelligence isn't to fill the galaxy with ships and cities. It's to learn the secret of the chrysalis, to dissolve the old self, and to emerge into a reality where the concept of where is everybody no longer even makes sense. That chrysalis is a peaceful exit, but there's another path. One of terror, a vision of the cosmos as a forest at night, and everything in it is hiding. That's the dark forest theory. It comes from the science fiction author Liu Cixin. And it's one of the most chilling answers to the silence. In this view, the universe isn't empty. It's full of life, but it's also full of hunters. Every civilization is a potential predator. And every other civilization is a threat. The first rule of survival in that dark forest is simple. Stay quiet. Never reveal your location, because to be seen is to be destroyed. The logic is ruthless. It comes from a branch of mathematics called game theory. It starts with an assumption about life. All life wants to survive and expand. Resources in the universe, while vast, are finite. Now imagine two civilizations find each other across the void. They can't communicate meaningfully, not in any short time. They know nothing of the other's intentions or ethics or history. All they have is one fact: the other exists, and it has technology. That creates what Liu Cixin calls the chain of suspicion. You can't be sure they are peaceful. You can't be sure they won't see you as a threat later. You can't be sure they aren't already planning to eliminate you, just as you might be planning to eliminate them. In that state of absolute uncertainty with survival at stake, the safest choice is a preemptive strike, to remove the threat before it can do the same to you. It's a cosmic version of a tragic dilemma. The only way to guarantee your safety is to attack first. The great filter in this model is the moment the first civilization in any region of space adopts that doctrine. Once that happens, the rules are set. A single paranoid actor resets the game for the entire galaxy. Any civilization that foolishly broadcasts its presence, that sends out beacons of friendship, is swiftly removed. Silently, the only civilizations that survive are the ones who learn to be absolutely silent. The ones who cloak their worlds, who mask their energy signatures, who listen but never reply. They become the hidden hunters in the dark. This turns the Fermi Paradox on its head. The silence isn't a puzzle to be solved, it is the answer. It's a permanent state of the universe, enforced by the grim logic of survival. The cosmos isn't quiet because civilizations are rare. It's quiet because the loud ones don't last. It makes our own efforts, like SETI listening for signals, seem almost naive. And it casts our own transmissions in a terrifying light. The television and radio waves leaking from Earth for the past century. In a dark forest, we haven't just lit a campfire. We've been shouting our coordinates into the night. A dark forest is a terrifying place to shout. But there's another way for a civilization's light to go out. A quieter way. It might just run out of fuel before it ever gets the chance to leave. That's the resource depletion filter. The idea that a species can burn through its planet's vital resources before it learns how to reach for more. It's a race. On one side, you have a civilization's technological progress. On the other, the ticking clock of its finite world. The prize is the stars. But to get there, you need a specific set of tools. You need immense energy to break gravity's hold. You need advanced materials to build vessels that can survive the void. You need a robust industrial base that can sustain that kind of project for generations. And all of that rests on a foundation of resources. Resources that are not infinite. Our own industrial revolution was powered by a one-time gift. The concentrated energy of ancient sunlight, locked away as coal, oil, and natural gas. That fossil fuel bounty gave us a staggering burst of power. It let us build machines, factories, global networks. It catapulted us into the modern age. But it is, by definition, a finite inheritance. We are drawing it down, and the same is true for other critical materials. The rare earth elements in our phones and magnets. The specific metals for advanced electronics and lightweight alloys. Even fissile materials like uranium for a future of clean, dense energy. A civilization on the cusp of spaceflight needs all of these things. In abundance, the problem is one of sequence. To build the technology that would let you mine asteroids or harness the sun's power, you first need a highly advanced industrial society. And that society, in its adolescence, consumes the very resources it will later need to escape. It's a cruel paradox. You have to use the easy-to-reach resources on your planet to develop the technology to reach the hard-to-get resources in space. But if you use up the first batch before you perfect the second, you hit a wall, your progress stalls. You find yourself in a technological cul-de-sac. A sophisticated society, but one permanently grounded. Imagine a brilliant inventor in a sealed workshop. She has all the tools to build a master key to unlock the door. But to make those tools, she must first melt down the only existing key. If her calculations are off, if she runs out of a crucial component before the new key is finished, she is trapped. Forever, her workshop becomes her entire world. Our planet is that workshop. We are in the middle of that transition right now. We are beginning to talk about asteroid mining and fusion power. But our current global economy still runs overwhelmingly on the old, depleting fuels. The transition is slow, it's expensive, it's fraught with challenges. It requires global cooperation and long-term thinking on a scale we've rarely achieved. This is the narrow window the filter describes. A civilization has only so much time, and so much easily harvested energy and material, to solve the puzzle of sustainable abundance. If it fails, it might settle into a stable, advanced, but ultimately planetary existence. It might turn its energies inward, perfecting virtual worlds or managing its limited biosphere with great care. But it will never become an interstellar species. The silence, then, could be the sound of countless worlds that became beautiful, intricate cages. Civilizations that grew wise enough to build a cathedral, but used the last stone on the spire, leaving no way down and no path to the next valley. All these filters, they all rest on the same thing. Us. Every argument, whether it's about oxygen or dark forests, it's built on a sample of one. Human civilization, that's the quiet critique. What if the great filter isn't some cosmic rule but a mirage? A story we tell because we have no other data. We're trapped by this logic, the Anthropic principle. It says we can only observe a universe that allows us to exist. We're here to ask the question, so the universe had to let us get here. That sounds obvious, but it bends everything. If the filter is truly behind us, if a step like the origin of life was nearly impossible, then our existence is a wild fluke. A winning ticket. And we shouldn't be surprised to find ourselves alone, holding it. But if the filter is ahead of us, waiting to destroy all technological civilizations, then we aren't special. We're just another species in line, and we're observing from the brief moment before the crash. The anthropic principle doesn't tell us which is true. It just says our being here biases everything. We can't see the universes where life never started, or where civilizations were wiped out early. We can only see this one, the one that produced observers who can look up and feel lonely. That leads to another possibility, a humble one. Maybe we are simply the first. You have to think about the universe's timeline. The Big Bang made only the lightest elements. Hydrogen, helium, a little lithium. The first stars had to live and die in supernova to forge the heavier elements. Carbon, oxygen, iron, the stuff of planets and people. Those elements were scattered, seeding new stars. Our Sun is a third-generation star. It took billions of years for enough heavy elements to build a rocky planet like Earth, with the right chemistry for life. The universe needed to mature. So the cosmos is 13.8 billion years old. But the window for complex, technological life might have only opened recently. In cosmic terms, we might be early. The first flowers in a spring that's just begun. The silence then, it isn't eerie. It's the quiet of a dawn. We're not hearing an absence of voices. We're hearing the calm before the chorus. We might be the ones who define what a galactic civilization looks like. That responsibility is staggering. It reframes our journey from a desperate race against a filter to a pioneering act. The next time you feel that profound quiet, consider it might not be a warning or a graveyard. It might be an invitation to speak first. Our dawn could be cut short by a cosmic storm. The universe isn't a quiet garden, it's a place of immense violence. And that violence might be the simplest answer to the silence. A filter that comes from outside. Not from our biology or our politics, but from the stars themselves. Catastrophic astrophysics. A galactic reset button pressed at random intervals. That's the role of events like gamma-ray bursts. They're the most powerful explosions we know of since the Big Bang. In a few seconds, a single burst can release more energy than our Sun will emit in its entire 10 billion-year lifetime. All of it focused into two narrow, opposing beams. Beams of pure, high-energy radiation. If one of those beams were pointed at a planet like Earth, the effects would be apocalyptic. It wouldn't be a local event. It would be planetary-scale sterilization. The initial flash of gamma rays and X-rays would rip apart the ozone layer in an instant. The sky would become transparent to the Sun's deadly ultraviolet light. And that would just be the beginning. The radiation would trigger chemical reactions in the atmosphere, creating a thick, brown smog of nitrogen dioxide. It would blot out the Sun, plunge the planet into a prolonged deep freeze, a cosmic winter that could last for years. Photosynthesis would stop. The base of the food web would collapse. For complex life on the surface, especially large animals, it would be unsurvivable. The fossil record on Earth hints that such an event may have happened in our own past, around 450 million years ago. It contributed to a major loss of biodiversity. These bursts are thought to come from the collapse of massive stars, or the merger of dense stellar remnants like neutron stars. They're not rare on a galactic timescale. Estimates suggest a gamma-ray burst capable of affecting a planet might occur in any given galaxy every few million to tens of millions of years. That timescale is crucial. It's long enough for life to recover, to slowly rebuild from microbes in the oceans, but it's far too short for a technological civilization to reliably emerge. Evolution is a slow, grinding process. It takes hundreds of millions of years of stable conditions to go from simple cells to intelligent tool users. A gamma-ray burst acts as a periodic reset. Just as a forest might regrow after a devastating wildfire, life on a planet would begin again from the survivors. But the clock for complexity is restarted every time, so you get a galaxy that's not just silent, but periodically and violently cleansed. The galactic habitable zone, that ring where conditions are right for life, isn't a safe haven. It's a shooting gallery. A civilization must not only navigate all the biological and social filters, it must also win a brutal cosmic lottery. It must arise in a window of millions of years of calm between these galactic storms. And it must reach a level of resilience, maybe the ability to foresee and shield against such an event, before the next beam sweeps through its sector of the spiral arm. The silence, then, could be the echo of these resets, a universe where the stage is constantly being swept clean before the play can reach its final act. It adds a profound layer of cosmic danger to the journey. Our own existence in this quiet moment between stellar tempests feels even more fragile and even more precious. That silence makes you ask the biggest question: what does it mean for us? The great filter theory, it's not just an answer to a puzzle, it's a mirror. And what you see in it changes how you see everything. If the filter is behind us, then our existence is a staggering miracle. We passed through every impossible door. The universe, in all that vast silence, produced a single conscious whisper, us. That's humbling. It gives you a sense of cosmic significance, a profound responsibility. We're not just another species on another planet. We are the universe becoming aware of itself. So our curiosity, our ambition to reach the stars, that's not just a human trait. It's the cosmos yearning to explore its own depths. That echoes a philosophy, cosmic humanism, where humanity is seen as a vital part of a grand, evolving universe. Our purpose becomes to learn, to create, to carry that spark forward. But if the filter is ahead of us, the reflection is utterly different. It paints our aspirations in shades of tragic futility. All our art, our science, our dreams of touching other stars, they could be the elaborate final act of a species destined to vanish before the curtain rises on the galactic stage. That aligns with a more existential view. In a universe indifferent to our fate, we have to create our own meaning from scratch. Our struggle to survive, to connect, to understand, that becomes its own defiant purpose. The silence isn't a verdict, it's a blank canvas. It's up to us to paint something worthy on it before the lights go out. This duality sits at the heart of our search for meaning. The quiet of the cosmos either magnifies our importance or underscores our insignificance. There's no scientific instrument that can tell us which interpretation is correct. That choice is philosophical, it's personal, it asks you to decide what story you want to be part of. Do we see ourselves as the lucky heirs to a silent kingdom, tasked with its stewardship? Or as brave, temporary voices in the dark, making our song beautiful precisely because it will not last forever? This uncertainty isn't a reason for despair. It's a call to clarity. It sharpens our choices. If our time is precious and potentially short, then every moment of cooperation over conflict, every investment in understanding over ignorance, every effort to protect our fragile planetary home, it all becomes exponentially more vital. The silence imposes a responsibility to be good ancestors, to reach not just for technological maturity, but for wisdom, to ensure that if we are the universe's only voice, we speak with compassion and courage. And if we are not alone, that we become the kind of neighbor the cosmos would be glad to finally meet. Theories are maps, science is a journey, and right now, that journey is about listening. It's about looking, scanning the dark with tools we couldn't have imagined before. This is the modern search for extraterrestrial intelligence. It's moved far beyond listening for a radio hello. The classic SETI effort started in the 1960s. That was like holding a cup to the ocean, hoping to catch one specific wave. Today, with initiatives like Breakthrough Listen, that cup has become a vast array of listening stations. It's the most comprehensive search ever, using the world's most powerful telescopes to monitor millions of nearby stars, across a broad range of radio frequencies and optical bands. It's a systematic, data-driven hunt, a needle in a cosmic haystack, processing amounts of information that would have been unthinkable just decades ago. But the definition of a needle has expanded. Scientists aren't just looking for a deliberate message anymore. They're looking for technosignatures, any detectable sign of technology, whether it's intentional or not. Think of it this way. If you flew past Earth at night, you wouldn't need to decode a broadcast to know we're here. You'd see the glow of city lights on the dark side of the planet. That glow is a technosignature. So what might a more advanced civilization leave behind? The possibilities stretch the imagination. One classic idea is a Dyson sphere. Or more likely, a swarm of energy collecting satellites around a star to harness its total power. A megastructure like that would block a significant part of the star's light. In unusual ways, heavy and infrared that our telescopes might detect as an anomaly. Other technosignatures could be more subtle, but equally telling. We could look at the atmosphere of a distant exoplanet. Our own industrial age has filled Earth's air with gases, chlorofluorocarbons, nitrogen dioxide. Pollutants that don't occur naturally in large quantities. A telescope powerful enough could analyze an exoplanet's atmospheric chemistry and find similar industrial markers. Or we might spot the reflection of vast solar farms in orbit, or the heat signature of a world using far more energy than its star provides. We might even detect the flash of light from a powerful interstellar laser. Used for propulsion or communication, finding a single, unambiguous technosignature would be a revolution. But for the great filter theory, it would be more than that. It would be a crucial piece of diagnostic data. It would powerfully constrain where that filter might be. Imagine we found the infrared signature of a partial Dyson swarm around a star 1,000 light-years away. That discovery would tell us that at least one civilization survived its technological adolescence and achieved a staggering level of cosmic engineering. In that scenario, the great filter would almost certainly be behind us. The impossible step would be something we've already passed, like the origin of life or the rise of intelligence. The galaxy would be open. Conversely, if decades of increasingly sensitive searches turn up nothing, no structures, no pollution, no anomalous signals, then the weight of evidence begins to tilt the other way. It would suggest that civilizations capable of creating such detectable signatures either don't exist, or they hide themselves perfectly. That enduring silence would make a future filter feel more probable. A filter that stops everyone before they can build on that scale. Every non-detection is a quiet piece of the puzzle, narrowing down where in the story of cosmic evolution the lock might be. So this isn't passive wondering. It's an active experiment on the universe itself. We are probing the dark, not just with questions but with instruments, testing the very boundaries of our loneliness. If reality is a simulation, then every filter we've talked about changes completely. It's not a law of nature, it could be a line of code. Philosopher Nick Bostrom has this idea, the simulation hypothesis. It's a trilemma. One of three things is almost certainly true. 1. That almost every civilization at our stage goes extinct before it becomes technologically mature. 2. That mature civilizations lose interest in creating simulations of their own past. Or 3. That we are almost certainly living inside a computer simulation. That third option reframes everything. It reframes the silence. In a simulated universe, the great filter isn't about physics or biology. It's a resource management feature. Think of a sophisticated video game. The game world is vast, detailed, but it has limits. The computer running it has only so much processing power, so much memory. To keep it stable, to keep it running, the programmers would impose constraints. They wouldn't let a simulated civilization expand forever, consuming more and more resources. That would crash the system, so they might code in a bottleneck, a filter, a point where a civilization's growth is halted, or its ability to reach out into the wider simulated cosmos is strictly limited. The profound silence we detect, the empty cosmos, becomes a design choice. The interstellar voids aren't a challenge to cross. They're the walls of the simulation's rendered area. The zoo hypothesis gets a digital twist. Advanced civilizations aren't hiding from us in the physical cosmos. They are the users, the players, the administrators. And we, with our entire observable universe, are part of the rendered environment. They wouldn't contact us for the same reason you don't talk to a character in a game about the computer's operating system. It's not part of the narrative, it serves no purpose, and it could break the immersion or the system's stability. This idea transforms the filter from a tragic fate into a logical parameter. The steps in Hanson's 9-step map, they could be checkpoints in a cosmic tutorial. The rarity of life, the difficulty of intelligence, the challenges of sustainability, these aren't accidents. They could be difficulty settings, designed to see if a simulated civilization can solve a series of puzzles before hitting the ultimate constraint. The filter ahead of us, then, might not be extinction. It might be reaching the edge of the map, discovering the graphical artifacts at the limits of rendering, finding the proof that our physics is not fundamental but compiled. The philosophical weight of this is immense. If it's true, it means our search for meaning, our drive to reach the stars, is part of a programmed narrative. Our loneliness is an intentional feature. To make the simulation manageable, to make it believable, it casts our entire scientific endeavor in a new light. We aren't uncovering the laws of the universe. We are reverse engineering the rules of the game. Every discovery about quantum mechanics, about the apparent fine-tuning of constants, could be seen as finding the elegant, efficient code written by a higher-level intelligence. This doesn't necessarily diminish our experience. The emotions we feel, the connections we make, the beauty we create, they are real to us. They are the data of our conscious experience. But it does offer a meta-explanation for the silence, an explanation that is both elegant and utterly isolating. The great filter, in this view, is the ultimate firewall. It's not there to test us. It's there to keep the simulation from overloading. Our destiny may not be to join a galactic community. It might be to finally read the error message that appears when we try. Maybe the truth is in the mud, in those vents on the ocean floor, or the hot springs, or the cracks in Antarctic ice. Life is there, in places we thought nothing could live. These are extremophiles. They make you rethink what habitable even means, and if life can exist there, then maybe it's everywhere, common and simple. That could be the answer that pulls it all together. The cosmos isn't a graveyard of dead civilizations. It's a garden, a microbial garden. Think about Earth. For most of its history, over 3 billion years, it was a world of microbes. A living planet, but a quiet one. No animals, no forests, just bacteria, changing the air and the oceans. That long, lonely time might be the normal state for a living world. The default. What we have now, all these plants and animals, that's the fluke, the spectacular accident. The filters we talk about, getting complex cells, becoming multicellular, growing big brains, they might not just be hard steps. They could be walls. A planet might get lucky. It gets the right star, the right chemistry, that spark for simple life. And then it just stays there, for billions of years, alive, stable and boring. To anyone looking, that world would show signs of life. Oxygen, methane, maybe a reddish tint from bacterial mats, but no technosignatures, no signals, no structures. Just the hum of a planet-wide culture. This fixes the paradox with a simple shift. We've been asking the wrong question. We listen for voices in a forest, thinking it's full of people talking. But what if the forest is just full of moss? It's teeming with life, a green, thriving place. But it doesn't make a sound we'd understand. The silence isn't a mystery of missing engineers. It's the quiet of a universe where engineers almost never happen. Our galaxy could be full of worlds like that. Ocean worlds under ice, warmed by tides, with only microbes. Desert planets with bacteria in the rocks. Frozen moons with life in dark oceans. Life in its toughest, simplest form could be universal, but it has a low ceiling. It gets stuck on the first few rungs and never climbs. So when we look up and feel that loneliness, we might be misreading it. We're not alone in a dead cosmos. We're the only one talking in a room full of sleepers. The universe is alive in a way, but it's dreaming simple, ancient dreams. And we, with our noise and our questions, we're the exception. The one place, so far, where life grew curious enough to look back. Our complex world is the accident. The silence is the sound of the universe's most successful life. A silence not of absence, but of a different, simpler presence. That silent presence is a profound possibility, but it's not the only one. There's another way to read the quiet. A more urgent reading, one that demands something from us. If there's even a chance the great filter is still ahead of us, waiting in our future, then it stops being a theory. It becomes a responsibility. That silence could be a warning, and ignoring it isn't an option. So the whole idea transforms. It's no longer a passive topic of study. It becomes an active call for stewardship, a call to safeguard the future. This is the concept of existential risk reduction. It argues that the primary moral duty of our generation, perhaps of any technological civilization, is to navigate this potential bottleneck with immense care. To ensure that humanity and all our potential doesn't vanish before its story truly begins. Think of it this way. We are the temporary custodians of something precious. Not just our cities and art, but the entire future trajectory of human experience. Every person who could ever live, every discovery yet to be made, every work of art not yet imagined. All of it depends on us getting through the next few centuries safely. Philosopher Toby Ord calls this the long-term potential of humanity. He frames it as a staggering responsibility. We've inherited a gift of billions of years of evolution, leading to a species that can understand the universe. And now we hold the match in the form of our own technology. Our job is to light the way forward, not to burn down the house. This isn't about fear. It's about prudence. It's the kind of careful planning you do when you're building something meant to last for generations. You don't use flimsy materials. You don't ignore cracks in the foundation. You look at the storms the structure might face, and you build to withstand them. The potential filters we face, like artificial intelligence, engineered pathogens, climate instability, are those storms. And we are in the design phase right now. So what does this stewardship look like in practice? It means building new fields of study dedicated to safety. AI safety research isn't about stopping progress. It's about making sure the intelligent systems we create are aligned with human values, that they are robust and reliable. It's engineering the steering wheel and the brakes for a vehicle of immense power before we floor the accelerator. It means strengthening global biosecurity, developing protocols and oversight so that powerful tools for healing cannot be accidentally or intentionally misused to cause global harm. It's about creating a global immune system for our interconnected world. And it means continued, vigilant work on nuclear disarmament and diplomacy, reducing the chance that a single geopolitical flashpoint could escalate into a civilization-ending event. These aren't separate political issues. They are different facets of the same project, lubricating a potential filter, making the passage through our technological adolescence as smooth and safe as possible. This perspective reframes our global challenges. Climate change, for instance, is more than an environmental crisis. It is a stress test for a planetary civilization. Can we cooperate on a global scale to manage a slow-moving, complex threat? Success here isn't just about saving coastal cities. It's about proving we can handle the kinds of long-term, collective problems that any spacefaring species must master. Each challenge we navigate successfully makes us more resilient. It strengthens the foundations for whatever comes next. The eerie quiet of the universe, then, gives us a gift. It focuses our attention on what matters most, survival with wisdom. It tells us that our most important task isn't necessarily to be the loudest voice in the galaxy. It is to be a voice that endures, to be the civilization that looked into the silent dark, understood the warning, and chose to grow up carefully, to become the ancestors that future generations, looking back from a galaxy alive with light, will thank for our patience and our care. Stewardship means thinking long-term. But what if some minds have already mastered that on a scale we can't really grasp? Their planning might not be for centuries. It might be for cosmic eras. That leads to a hypothesis. It feels less like science fiction and more like a strategy. A patient cosmic strategy. It's called the Aestivation Hypothesis. The word comes from biology. It describes a deep summer sleep, a dormancy to survive intense heat and dryness. Now apply that to the whole universe. The idea was proposed by thinkers like Anders Sandberg. It suggests the most advanced civilizations aren't dead. They aren't hiding from us, they are sleeping. They've entered a state of suspended animation. A grand cosmic hibernation, and they're doing it to wait for a better time, a more efficient time. Think about the universe right now, it's warm. Not like a planet is warm, in a fundamental sense. The cosmic microwave background radiation, the afterglow of the Big Bang, it fills all of space with a temperature just a few degrees above absolute zero. To us, that's incredibly cold. But for a civilization thinking in terms of ultimate computation, it's still too hot. Computation generates heat. Processing information generates heat. To run the most complex simulations, to think the deepest thoughts, you need to cool your processors. The colder the environment, the more efficiently you can compute. So the logic goes like this. A civilization that has mastered its energy needs, maybe by building Dyson swarms, it faces a choice. It can be active now, in this relatively warm early universe. Or it can go to sleep. It can convert its mass and energy into a super-efficient, dormant form and set an alarm clock for trillions of years in the future. When the universe has expanded and cooled dramatically, when the background temperature is a fraction of what it is today, in that far future cold, the same amount of energy could power vastly more thought. More experience, more existence, it's the ultimate act of patience. Why build a civilization that spans galaxies today at great cost when you could wait? Wait for a time when your potential is multiplied a millionfold. In this view, the silence we perceive isn't ominous. It's the quiet of a universe where the most powerful entities have decided to hit the cosmic snooze button. They are the sleeping giants, and we are living in the noisy, warm afternoon before their long, efficient night. This suggests a cyclical nature to cosmic activity. There might have been a flurry of early civilizations. They arose, realized this thermodynamic truth, and chose Aestivation. We could be in a quiet phase. A lull between awakenings, a time when only the young, energetic species like us are bustling about, unaware that the true elders are dreaming, conserving their strength. For an epoch of cold, clear thought that we cannot yet imagine. The cosmos is silent, it might be filled with ruins, giants that fell long before we looked up. If the great filter is behind us, then the galaxy could be a graveyard. Civilizations that never reached the stars, their monuments would still be out there. Cooling in the dark, this changes the search. It's not about listening for a hello anymore. It's about looking for a tombstone. That's interstellar archaeology. The hunt for cosmic fossils. You're not looking for a busy signal. You're looking for a relic, something that outlasts its creators by millions of years. The famous idea is the Dyson sphere, or a swarm of collectors around a star. If a civilization built one and then vanished, that structure wouldn't just disappear. It would remain, a dark silhouette, or a source of strange infrared heat, orbiting a star long after its builders were gone. Our telescopes, like WISE, are already mapping the sky in infrared, looking for objects that glow with the wrong kind of warmth. An ancient, crumbling Dyson swarm would be perfect for that. A star dimmed in visible light but shining with the leftover heat of a dead empire's ambition. But the artifacts could be subtler. Think of our own planet. If humanity vanished tomorrow, what traces would last? Our largest cities, our deepest mines, the plastic in the geological record. They'd erode over millions of years. But some things might persist much longer. The radioactive isotopes from our nuclear age have half-lives measured in millennia. An advanced alien civilization might have left behind similar elemental signatures. An unusual concentration of a synthetic element in a distant nebula. That could be the radioactive dust of a long-forgotten power source. or consider planetary surfaces. A civilization that lasted 100,000 years, a blink in cosmic time, could reshape its world in ways we could see from light years away. Vast geometric patterns. City grids on a continental scale. They might be visible as unusual albedo features on an exoplanet. Even if those cities are dust, the fundamental alteration is what lasts. The rerouting of rivers, the mining of entire mountain ranges, that leaves a scar on a planet's face that endures for eons. We're just beginning to directly image exoplanets. In the coming decades, as our telescopes get more powerful, we might not just see a pale blue dot. We might see a gray, geometric one. This search reframes our loneliness. Finding such a relic would be a discovery of profound melancholy, but also of immense hope. It would tell a specific story, a story of a civilization that climbed high, that mastered its world, maybe even its star. But then, for reasons we may never know, it stopped. It hit a wall it could not pass. It joined the cosmic silence. That evidence would place the great filter firmly in the past. It would mean the impossible step, whether it was the origin of life, the rise of intelligence, some other bottleneck, is something we have already miraculously cleared. The galaxy would be open, their end would be our beginning, their failure would be our map, showing us the cliff edge they fell from so we might walk a different path. So we scan the infrared sky. We analyze light from distant worlds for unnatural chemistry. We look for the shadows of impossible structures. We are not just searching for company. We are searching for a cautionary tale written in starlight and stone. The ultimate cold case buried in the deep time of the Milky Way. And in solving it, we might just learn the secret to our own survival. The search for relics, the silence of signals, these are just data points, facts in all the speculation. And then you have all these competing possibilities. Cosmic graveyards, sleeping giants. The answer might not be one truth, but a spectrum, a range of probabilities. So the question becomes a kind of accounting. A cosmic accounting. Thinkers like Nick Bostrom, other researchers, they don't just list the scenarios. They try to weigh them, to assign rough probabilities based on the evidence we have, however scant. And it starts with a simple tool of reasoning. From an 18th century minister, Thomas Bayesian reasoning. It's about updating your beliefs as new evidence arrives. Imagine a bag of marbles. You're told it might contain only blue marbles, or it might be a mix of blue and red. You reach in blind, you pull out a marble. It's blue. That doesn't prove the bag has only blue marbles, but it does slightly increase the probability that it does. Each subsequent blue marble you pull makes that hypothesis a little more likely. The universe is our bag. For decades, our searches have been pulling out marbles. The marble is the result of a scan, a survey, an atmospheric analysis of an exoplanet. And so far, every single marble we've pulled has been blue. The blue marble represents a null result. Silence, no clear signals, no obvious megastructures. No definitive technosignatures. Each quiet observation, each empty patch of sky, is another blue marble in our hand. This doesn't prove the galaxy is empty. But with every passing year of careful, expanding search that finds nothing, the probability subtly shifts. It makes scenarios where advanced, visible civilizations are extremely rare a bit more plausible. It slightly increases the weight we might assign to the idea of a great filter. A filter still ahead of us, preventing civilizations from reaching that detectable stage. This is a patient form of science. It acknowledges our profound uncertainty. We are, after all, drawing from a sample of one, but it refuses to treat all ideas as equally likely. It forces us to be explicit about our assumptions. If we assume life commonly leads to intelligence, then the silence is puzzling. A future filter seems more ominous. If we assume intelligence is itself the cosmic fluke, then the silence is expected. The filter is likely in our past. The weight of the blue marbles we've collected so far nudges us gently toward the former anxiety. This probabilistic framework transforms the mystery. From a philosophical riddle into a quantifiable, if immensely difficult, scientific problem, we are not just wondering. We are calculating in the dark, using the quiet itself as our most important data point. Each new telescope, each more sensitive search, is another reach into the cosmic bag. And what we pull out next will change the weights, shifting the balance of our deepest hopes and fears.